Okay, this one's it's a little messy the way I have this written there, just because I was trying out some things, just trying to learn a few things for myself there. But I will explain this one. We'll go through this one. This one isn't all that bad for us right there. All right, so we got this Taylor series, gives us the nth derivative formula, and then we want to write the first four non-zero terms and the general term for the Taylor series for f about x equals 1. All right, so all I'm going to do, there's nothing to start with other than your main definition here. So I'm going to start with that main definition. It tells us the center is equal to 1, right? So I'll go f of 1, f prime of 1, x minus 1 to the first over 1 factorial, f double prime of 1, x minus 1 squared over 2 factorial, f triple prime of 1, x minus 1 cubed over 3 factorial. So there we go. There's like my first four terms there. Unless I get 0 for one of them, then I'm going to have to add in another one because it says right the first four non-zero terms. And then it tells us f of 1 was 1. That's given right there. And then it also tells us that prime of 1 is equal to a negative 1/2. So that's where that came from right there. And then I didn't know the second derivative at 1 or the third derivative at 1, but it says the nth derivative is given by this equation here. So when I wanted the second derivative, that's plugging in 2 for the n. So negative 1 squared was a positive 1, then 2 minus 1 was 1 factorial, and then 2 squared was 4. So I got 1/4 for that. That's where that positive 1/4 came from, and then there's your 2 factorial that carries down. Then the third derivative, we're plugging in 3 for the n. So 3 minus 1 is 2 factorial. Negative 1 to the third is a negative number. And then you got 2 to the third, which is equal to 8. So negative 2 over 8 reduced to negative 1/4. That's where I got that was negative 1/4. And the 3 factorial carries down. So we could probably just kind of leave it like that, but I just simplified it. The numbers were small enough. I just simplified that pretty easily there. And there are the first four non-zero terms that they asked for. And so that I thought was pretty straightforward. You start with your main definition, find the first four terms. What the tricky part is where I thought it was tricky, but there's an easy way to do this general term for the Taylor series. If you're trying to stare at the patterns, it's really difficult to even like your brain would even go here to see the patterns there. Like you could rewrite the a as 4 times 2 and as 2 squared times 2. You could rewrite that as 8 times 3 and as 2 cubed times 3 to get this 2 to the n to the n. Like that's weird. Okay, let me kind of share with you real quick how you can get this general term. All right, now think about this. So we did the first derivative, x minus 1 to the first over 1 factorial. Then we did the second derivative, x minus 1 squared over 2 factorial. The third derivative, x minus 1 cubed over 3 factorial. So if I was doing a general thing, it would be the nth derivative, x minus 1 to the nth over n factorial, right? And so automatically it's going to be x minus 1. It's going to be x minus 1 to the nth over the n factorial. Like that's going to be there. And then what's out in front of here, instead of the third, it's going to be the nth derivative right there. So that's like our general thing that we're going to use here. Now, they gave us what this f sub n, fn was, okay? That's what I'm going to plug in right here. So this is your derivative. This is part of your, your formula when you're doing your main definition, your Taylor polynomial. So all I'm going to do is take that and put that in right there. So I'm going to have negative 1 to the n minus 1 factorial over 2 to the n. And then that's your derivative, right? Your third derivative, fourth derivative, fifth derivative. And that's all in front of this stuff right here from your Taylor polynomial definition, x minus 1 to the n over n factorial. And then what we could do with that is we could rewrite this, simplify these factorials like we do when we did our ratio test simplification here. You can make this n times n minus 1 dot, all the way down to 1, which is n minus 1 factorial. So those n minus 1's factorial canceled out. So what you're left with here is the negative 1 to the n carries down. The x minus 1 to the n is still there. And then you have this 2 to the n times n factorial. And there is your general term that we have the same exact thing. We got that right here for the general term. Now, if you had some issues getting that, we didn't use that general term through the entire rest of the problem. So, I mean, you would have gotten all those points for that. You would have gotten all the other parts of the problem there. You just would have messed up that a little bit. You're still in really good shape there. But if you see a general term and if you see a derivative, usually you take the derivative of the original function, or you see an integral, you do the integral. And then I just had to remember, like, my general derivative is that stuff right in front of all that other stuff right there. So that's why I kind of thought to do that. And then just threw that in right there because it's too difficult to kind of notice what the patterns are. Unless your brains work that way and you can see the patterns really easily, that's a little trickier for me sometimes there. So I like to have that more systematic approach there. So there's letter A. Now letter B, I just kind of did some extra work down here. All this work right here is unnecessary. But I did some extra work down there just kind of prove myself something. Um, but when it tells us the radius of convergence is 2, okay, here's what we're allowed to start with is the absolute value of x minus c is less than that radius of convergence. So if they tell us radius of convergence is 2, I can start right there. That's what I'm allowed to do. So we kind of know that going forward there. So they told me the center was about 1. So my c was 1, and then they told me the radius of convergence was 2. So you're allowed to start right here and go straight to that step where you're going to do your lesson sandwich, and then you have your integral of convergence. And then remember, you got to check the endpoints, which we got to do. So all this really letter B was starting with that, and really it came down to checking your endpoints. It was just a basic lesson sandwich and checking the endpoints. Now, I remember when I first worked this out, though, I wasn't sure. I wasn't like 1,000% certain that I could do that. So I actually did my ratio test like we did on some other problems. I did my ratio test with that power series, did the normal thing, force it to be less than 1, and then I got down to this point anyways, which is when then I knew that we're allowed to start with that. So that was all just kind of completely unnecessary. You still get to the same point, but it's just nice to know now that we can just start right there. All right, and then the bottom line, this one was just checking your endpoint. So you'll get so much credit for that. And then let's check the endpoints there. So you're going to take this -1 and the 3. And I guess we are using, Michael, I said we weren't using this general term. You did use the general term for part B, but you didn't use the general term for C or D. So you would have messed up part B, but you still would have had all these points and you had all your full credit for part C and part D. So my bad on that. But when you plug in -1 for that X right there, okay, here's where I'm plugging that in for those X's. I get -1 minus 1. That gave me a -2 to the n, and everything else just carried down. And then remember what we said in our extra video lectures there. You can rewrite that thing as -1 to the n times 2 to the n. And then you also have this extra -1 to the n. So that's -1 to you're going to add up those exponents. So that's -1 to the 2n, which is always even, which means that thing is always positive, and then those 2 to the n's will always cancel out. That's a divergent p series because you just get 1 over n right there. And then when you take x equals 3, plug that in for that x right there, that -1 to the n is already there. You get that 2 to the n right away, which cancels out. And then you have -1 to the n over n. When you could go straight to, if you kind of do this work in your head, I kind of threw that out in there. You know, if you wanted a refresher of what that alternating series test was, you know, you do the limit as 1 over n approaches infinity of 1 over n, that's 0, and then 1 over n, so n plus 1 is less than 1 over n. That's true since that n plus 1 is greater than n. So that is your alternating series test, but you're welcome to do that in your head. And just as long as you get that converges alternating series, since that diverges and converges, that means it's a parentheses at the -1 still, but then it goes to a bracket at that 3 right there. So it's just practice checking those endpoints right there. And then C and D are things that we've done quite a bit. All right, so we got a Taylor series used to approximate f of 1.2. So you're going to take the 1.2 and just plug it in place for x into your Taylor series. That's what it is. That's what the Taylor series is. It approximates that y value on your actual curve right there. Now it says use the first 3 non-zero terms. So I just need to use those first 3 terms right there. So that's why I jotted those down. And at the same time, I'm plugging in 1.2 for those x's. And then what I did when I got 0.2, I made it 2/10, which is like 1/5. And then so I kind of converted the fractions right there, and then you can practice the arithmetic on your own and kind of get that number there. But convert it with the fractions. The decimals are a little bit goofy. And then letter D says, show it your approximated answer is within 0.001 of that exact answer. So that's like 10th place, 100th place, 1000th place. That's 1 over 1,000. You know, they're talking about the difference between the approximated and the exact answer. And then notice you do have this alternating series, and it goes 1/2, 1 over 8, 1 over 24. So those things, you know, are getting smaller there. So this is your alternating series bound where you're just going to look at the next term. You don't see anything about Lagrange or anything like that. You're just going to do the next term. So since this one has just use the first 2, and then send you for that, that's why I have you find 3, use the first, or have you find 4, use the first 3, and then you use that 4th term that you haven't used yet, just the absolute value of that. So I just wrote that down, that next term in the pattern, and then I plugged in that 1.2 for the x. And then I had to kind of go over to the side and kind of do some basic arithmetic. If the numbers ever get too large, you could just kind of leave it like that and then just make a note that it's still 1 over, that's less than that 0.001 number or less than that 1 over 1,000 number right there. But I just kind of had the time, so I did some arithmetic and got that 1 over 1,000 there. So I thought that general term was a little bit tricky, but I'm grateful that we get to see just how to do the general term with the more systematic approach right here. Pajamas. Jammies.